So for language, how do we go beyond fixed dimensionality input or context representation to model the influence of variable length contexts, contexts that might be indefinite in history length, like sentences or even more than sentences, multi-sentence discourse? And to do this, we're going to draw inspiration from the nature of human language processing. Human language processing unfolds in time. It is real time. It is incremental. And so fundamentally, at some level, there must be a uniform representational space that allows us to take previous inputs, integrate them together, and continually update as new inputs come together. And that representational space not only has to be what's going on at the current moment, but it has to encapsulate your memory for previous content as well. If we take that as inspiration for an architecture, we fundamentally get the following kind of picture. So we have a sentence, and as time goes on, as we're listening or reading, we have new inputs coming in. And there is some uniform representational space. So this sort of cell here, or this unit, is going to be representing in a constant format, but with time-varying contents, the representation both of the preceding history and of the effect of the current input on that history and on the context representation. So that's going to be our uniform representation of the sentence incrementally, and that's going to be continually perturbed as we have new inputs coming in, modulating that context. This is fundamentally not different from a representation of an incremental parser like incremental trees, but what's different is the nature of the representation that we're going to posit. Okay, and this is the first version of this that we're going to look at is the simple recurrent network. This is now quite an old proposal, but it was a hugely influential proposal in cognitive science. And I've formatted it for you here using a representation similar to what you saw for the multi-layer XOR network, but the shape of the architecture is a little different. I also want to emphasize that I'm not showing the bias nodes, which have a constant value of 1 here, but they're implicitly there both in the input layer and in the hidden layer. Okay, so what is the representation and structure for a simple recurrent network? First of all, we have the input. So at time 0, a word comes in, and a word is going to be represented as a vector of node values, as you saw before, say for the neural n-gram language model. And that vector, that is a constant representational format, but it's going to have different values. For example, for the preceding word, in the general case, that preceding word will have a different, it will be a different word than the current word. And so these are going to be different from each other. But the format, the representational format as a real valued vector is going to be the same. Next, we have the context layer. So at a particular time, this representation, which is sometimes called the hidden layer, and we're going to call it the hidden layer as well, the hidden layer of the previous time step is going to be used as the context for the processing at the current time step. Notice that these nodes are indexed with their time step here. So this is the time step 0 input x. This is the time step -1 input x. And this is the time step -1 hidden layer h. So this is h sub t minus 1. That is going to serve as the context input for the hidden layer h at time 0. So you'll notice that both the hidden layer of the previous time step and the input of the current time step jointly come together to influence the representation of the hidden layer at the current time step. And that hidden layer at the current time step is that uniform sentence representation, okay? And what does that uniform sentence representation do in the simple recurrent network? It has a goal of predicting the next word. First of all, I'll show you the update rule. So this is the update rule that the hidden layer at time step t is going to be it's going to be formulated as follows. First of all, we're going to take weight matrices, U and W, and we are going to multiply them through with the context layer or the hidden layer at the previous time step and the input at the current time step respectively. We're going to sum them, and then we're going to pass them through a nonlinear activation function as we did before, okay? And that's going to give us our current time step hidden layer. And then the role of the hidden layer at the current time step is to predict the word that is going to come next, the word that is going to come in at the next time step, okay? In practice, this is going to be t plus 1. So if time step is 0, then this is going to be w1. But what the model is trying to do is it's always trying to predict what that word was. So you'll notice that that word and this word have the same variable ID because that is exactly what they're going to be. Okay, they're going to be the same thing. But this is prediction. This is influence once that word that may or may not have been well predicted comes in. Okay, and the next word prediction rule is that we're going to define a set of quantitative predictions. So this is like the ADAs of the nonlinear classifier for the exclusive OR network. And then we're going to do a softmax of that set of predictions to define a conditional probability distribution of the word given the context. So notice that in this model, everything that you need to predict the next word given the entire history is summarized in this hidden layer representation H. So H is this uniform sentence representational space. And that is the simple recurrent network. Here is another representation of the simple recurrent network that is sometimes called rolled up. Okay, and so this is going to be the input is F sub t, the hidden layer is H sub t, the output is the prediction of y. This would be y, what happens next. And then this is the context unit is H sub t minus 1. And what this arrow is doing is it's saying that as we go to the next time step, we're going to copy the hidden layer H sub t. And as we advance in a time step, that hidden layer will now become the context unit for the next time step. That's the rolled up representation. I just want to emphasize to you that that is equivalent to this unrolled representation that we saw before. Notice once again that the model is tuned, the weights in the model, which contain all the information, all the knowledge in the model, it's all in the weights. Those weights are fitted and learned to do next word prediction in the simple recurrent network. So let's look at a classic example that really brought the simple recurrent network to the attention of both people in machine learning and people in cognitive science 30 years ago. This is one of several examples in this classic paper, Ellman 1990. And this was a case of learning at the sentence level with artificial language input. So Ellman devised, this is a very small, just toy grammar that had a set of noun classes. It had, and verb classes, word classes. So there were nouns and verbs, and there were different kinds of nouns that had varying animacy and varying tendencies to do different things. And there were different kinds of verbs, some intransitive, some transitive. And then there were sentence templates. Okay, so for example, one template was that a human would eat some kind of food. Another would be that an animate noun would perform some transitive verb on some other animate noun. An aggressive noun might destroy some fragile noun and so forth. This is really just a toy fun example. But it turns out that you could learn very interesting things in a simple recurrent network approach with this kind of model. So this was an old paper, and at that point, word embeddings were not really integrated well into the language modeling neural networks literature. So Ellman used localist word representations, and what he did is he trained a simple recurrent network on a set of sentences from that toy grammar. And then what he did is he said, okay, so let's look for each word, let's actually look at what its average resulting hidden representation was, okay? And so what that means is, so suppose that these are 6 examples. Let's suppose that it was a corpus of just 6 sentences that the model was trained on. And once training happened, you would take all of the hidden layer representations after input from a particular word. So these are all the hidden layer representations, and after the word cat, and then you would average them all together. So you would take the average of these 5 representations, and we call that the average hidden vector resulting from the word cat. these two blue ones average would be the average hidden like representation from the word mouse. And then, so now you have one average vector per word in your vocabulary, and you can use some kind of clustering technique to look at the similarity structure of those. And it turns out that the word classes that were built into the model, or that were built into the grammar, are actually implicitly represented in the similarity structure of those vectors that is learned as a consequence of the model. So this was the similarity structure that was resulting. So this is just an agglomerative clustering method. And what you see is that the top level distinction was between verbs versus nouns. That's not surprising because verbs and nouns have the most different behavior. So for example, only nouns can be at the beginning of sentences. But you also see finer grained structure. So for example, cat and mouse turn out to be the very most similar words to each other. Animals were more similar to each other than to non-animal nouns. Animates were more similar to each other than inanimates, and so forth. And all of this was sort of semi-explicit, semi-implicit in the way that the grammar was defined. But the crucial point here is that then these facts fall out as a result of training this very simple architecture on sentences that are coming from that grammar. So that highly discrete, structured grammar implicitly leads to a quantitative similarity structure representation in vector representations of words that actually you can then interpret afterwards. So that's one of the first key results of the simple recurrent network model. And the simple recurrent network for quite a while was actually a real benchmark model in cognitive science, especially in the 1990s. However, the simple recurrent network has some limitations. In particular, you'll notice that in order to propagate information about a word far back in the sentence, so suppose that I have a word early in the sentence and I want it to influence processing much later on in the sentence. This happens with language because of hierarchical structure. I need to remember something about a word that may be very far back in linear space. That information has to be propagated very far through this hidden state representation. And there are a bunch of challenges that arise. There's the vanishing gradients problem that arose before, and simply the fact that whatever influence that word has to have on the hidden state representation has to be very robust, because all of the intervening words have an opportunity to perturb that hidden state representation. The fact that we need to do this in language is because of the hierarchical structure of language. Now, simple recurrent networks can learn that kind of hierarchy, but it turns out that it's not easy for them to do that. Their inductive bias is not well suited to do that, and we're going to see a specific example of that at the end of today. But before we do that, I want to show you a couple of other architectures that are also recurrent but have a little more structure, and that turns out is rather helpful for learning this kind of language-like hierarchy.